Alrighty, this may be a little hard to explain. I'll do my best, and it's hard to explain because it's a first of. What you're looking at there is a magnetic field diode setup. So we'll run through it as best as I can and try and correct any mistakes as I'm going, but hopefully you'll get the general idea of what's going on here. So we have a primary coil here, a secondary coil, and our field diode coil, which I'm going to call that. So our primary coil is being driven by my power supply at very low power. It's about 12 milliamps, 12.2 milliamps to be exact according to the scope, and we're running at 120 kilohertz at the moment. These are air core coils. Each one has 120 turns on them, so they're all one to one. So in normal transformer action, I've made this one smaller and wider because they're air core. The field tends to spread fairly rapidly, and if we had these thinner coils as our primary, the field would probably not even reach our secondary way back here. So a very low power at the moment, but it's just a test rig to see if the idea works. Now, MIT have made a mechanical magnetic field diode setup where they have coils, I think, spinning inside a drum, and that allows the magnetic field to induce the coil or the secondary, but doesn't allow it to come back. I wanted to achieve the same solid state, and this can be taken a whole lot further than this. This is just my first primary setup, and like I said, very low power. We're at about 12 milliamps at 14 volts, but we're only at a 15% duty cycle on the pulse. So not a lot, and we've got a fair bit of distance for air core coils between our primary here and our secondary here. As you can see, the LED is lit, surprisingly, but it is lit. So that gives us a starting point. So in a normal transformer, current flows through the primary, the magnetic field shoots off in all directions, but also passes through the secondary coil, which induces a current. So my primary coil is firing a north field into this secondary, and the LED is biased so that the current will flow when that north field hits the secondary. What would normally happen then is the secondary produces a counter EMF, and a magnetic field that opposes that which created it shoots back this way, and that shows up as the primary core having to work harder. So once a load is placed on the secondary, that load is reflected on the primary. The primary uses more power to drive that load, and the more we load the secondary up, the more it's reflected on the primary, which is what I wanted to get rid of. So my idea here was, before I built all this, my thought experiment was to have the primary shoot the magnetic field into the secondary. Current starts to flow through the secondary field will then start to head back towards the primary. Of course it doesn't do that, it just sort of builds up, which increases the load on the primary. But my idea was to have the secondary hit our field diode coil, and this would also produce a north on this side, stopping that field from imparting onto the primary. So the way we achieve this is this coil, we have another little LED here, and we bias this coil so that the north field can pass through this coil and no current will flow because the north is hitting this side of the coil. It'll flow through that coil, hit this coil. This will start producing its counter field that opposes this one, which is also a north, and that would start to head back, hit this coil conducts, and the magnetic field is contained within in between these two coils here, and stops it from hitting this coil once again. This means that with this coil activated, the load on the primary and the load on our field diode coil is not reflected back onto our secondary, the load on our secondary and our field diode coil is not reflected back on the primary because the magnetic field is trapped between these two coils. So we'll have a look on the scope and we'll see where we're at here. Okay, so channel 2, the blue channel, is across my CVR, and channel 1, the yellow channel, is across our LED. So you can see the current rising through the primary coil, and you can see that is when the LED is conducting. So our transistor then switches off and we can see a little back spike in our secondary coil. So our polarity is correct. At the moment we're using 12.2 milliamps, 12 to 12.2 milliamps RMS, and the RMS voltage across our secondary coil at the moment is 2.11 volts. So what we're going to do down here first is I'm going to place the LED across, which is also a diode as you know, across our field diode coil, and I'm going to do it the wrong way around, so as the magnetic field hits the base of this coil and then current will start to conduct. So what will happen there is this coil will induce this coil, but this coil will now kill the magnetic field to this coil. So when I place the LED into our field diode coil, we should see the secondary coil stop producing power. Our LED will go out. So I'll go ahead and do that. Okay, so we can see that our secondary coil LED has gone out. That is because the field diode coil is now blocking the magnetic field because we have the LED biased. So as once the north field hits our coil here, that then sends the opposing field back to our primary, and this will show up, like I said, it's only low power, but it will show up on the scope. We're now at 12.4 milliamps, so it's gone up 0.2 of a milliamp, but you can see the voltage across our LED on the secondary now has dropped right down, 1.27 volts RMS. We've nearly killed the inductive kickback spike. There's not enough voltage for the LED to conduct, and so now we have a normal transformer action happening between this coil and the primary. What I'm going to do now is turn this LED around so it conducts in the other way, and that induction will come from this coil here, which is the magnetic field heading back towards our primary. That would normally impede the primary and cause it to increase its power to keep the load on the secondary going. So I'm going to put this in the correct way now. Watch the brightness of this LED when I do so. Okay, oh, you can't see that little LED down there. Anyway, so now our primary coil has gone brighter. Our secondary coil is now producing more current, producing more power all up, and our little LED across our secondary is much brighter. And we can have a look at that once again. Oh, just by taking this out. So that's without our magnetic diode in play. And that is with the magnetic diode in play. So not only is our LED across our secondary much brighter, we also have this one going even brighter again. And if we have a look at the scope, we can see a number of effects. So we are still 12.2 milliamps now, even though we're driving two LEDs and much brighter than the primary LED was. Our inductive kickback spike has increased dramatically, and as you can see by the waveform, there's much more power going through that LED on the secondary than there was without our field diode coil activated. So I'll just disconnect the diode on the field coil. So that is without it. Our RMS voltage across our LED is 2.06, 2.07. You can see how long the LED is conducting here. Time scale 12.2 to 12.3 milliamps. I will now hook the diode back onto our magnetic field diode coil, like so. Now you can see that our LED on our secondary is conducting a lot longer. Our current hasn't changed. Our RMS voltage across our LED on our secondary is now 3.77 volts RMS. That is due to the LED now conducting longer, and also to the larger inductive kickback on that coil when that transistor opens. But no reflection upon our primary coil, even though we are now driving two LEDs quite brightly. I do have a lot of light going on in the shed, so they may not look very bright, but they are certainly very bright. And once again, where's my screwdriver? I'll disconnect it, and you can see now that's the primary is now inducing our secondary the best it can. Very little output. When we add our diode, you can see it is now a lot brighter, and absolutely no reflection on our primary coil. And that is because that coil is indeed acting like a magnetic field diode, and it allows the magnetic field to pass through this direction from our primary, but does not allow the counter field to pass back through and work against our primary. And the second effect is now the magnetic field between these two coils is quite strong, a lot stronger than this one here is putting out, in relation to the primary and the secondary. And we now can induce double the load. This one's actually a little brighter than this one, so we now have more than double the load of what we had and we do not see any reflection at all on the primary coil. So it all works like it should. Now the challenge comes in making a transformer that uses this that is very efficient. So this is not an efficient transformer, it's an air core transformer. Our coils are a long way apart. Magnetic field will be all over the place and not concentrated into the secondary. So I need to do this using steel laminates, perhaps even soft iron wire instead of copper wire. Trying to find that that's enamelled is quite difficult, but I'm sure we'll come up with something. That's what I wanted to show you. This indeed is working like a magnetic field diode. Our field can pass through this coil to our secondary, but the field from the secondary cannot pass through this coil and impinge on the primary. So it's a no load transformer is what you're looking at there, due to us being able to block that counter field from working against the field of our primary. Alright, that's it. It's bloody cold out here. I'm going inside. Thanks for watching, and I'll keep you up to date with all the progress made on this setup here, and hopefully we can make it a lot better. Hopefully we can get the efficiency over that 100% mark. Cheers guys.